Hi everyone. Today I'm going to explain about the in-length offset and rigid zone factor that can be used in the modeling phase of SAP 2000 and ETABS. So, fluent element are modeled as line element in finite element softwares and they are connected at the joint. However, actual structural member have finite cross-sectional dimensions. When two elements such as beams and columns are connected by a joint, there is some overlap. This is the overlap of the cross sections. So in many structures, the dimension of the member are large and the length of overlap can be a significant fraction of the total length of the structure. Suppose this is the length of the beams connecting the beams to column and the overlap is the called IOF or offset at node I, and this is the in-length offset of the structural members. This overlap is the in-length offset connecting to the beams and columns. So we may specify a in offset using the parameter this I offset and J offset, which is called in-length offset. Here in this figure, the in-length offset is I offset at node I and J offset at node J. If L is the total length from the center to center distance of the column or the connecting the beams and the column assembly, and LC is the clear length, then the LC equals to total length minus offset at in I and offset at in J. It means LC equals to L minus summation of offset at both ends. And this offset lies in the panel zone of beam column assembly. This is the panel zone. The junction of the beam column assembly is the panel zone in the structure. If the structural dimension, element dimension is quite small enough, the significance of this offset length is not much, but in case of large structural elements having large dimensions, there is the offset length at each connecting node should be considered in the analysis. Suppose LC is the length minus offset at in I and in J, and T is the model time period of the structure. T equals to 2 pi root 2 over m by k, where m is the total mass of the structure and k is the stiffness of the structure. And this stiffness value depends upon the length and properties of the structural element. Suppose for any cross-section element with a certain grade of concrete and steel, the value of EI is fixed, and if the length of the structure is increased or the structural element is increased, the value of K goes on decreasing. Suppose if L is increased, then the value of K is going to be decreased. And if the value of K is going to be decreased, then the model time period of the structure is increased. And the deflection of the structure is also depend upon this parameter. So if the time period of the structure increase, the deflection also increases. So we'll verify in the model as well later in ETABS. In order to consider the stiffness properties of the structure or realistic determination of stiffness of the structure, the in-length offset or the rigid zone factor should be considered in the analysis. Otherwise, if we do not consider this factor, there may be the alternation of the result, the deflection of the structure or the bending moment as well. So let me turn into rigid zone factor. And analysis is based on the center to center line or joint to joint geometry of the structure in ETABS. Suppose if we look into the ETABS, the modeling can be done with the line element for the structural elements such as beams, columns, etc. So while doing this modeling, the structure has definite cross section, although here representing as a line element. If we extrude this view, the actual dimension of the structure can be seen. So frame element may overestimate the deflection of the structure, deflection in some structures. So this is due to the stiffening effect, which we have discussed just now, caused by the overlapping section at a connection, and it is to be more significant in concrete rather than steel structure, as we know that concrete or RCC structure has a huge cross-sectional element, so it is likely to be significant in concrete rather than steel. And we may specify a rigid in factor for each element using a parameter rigid, which gives the fraction of each in offset that is assumed to be rigid for bending and shear deformation. And the length rigid offset starting from the node I is assumed to be rigid. And similarly from node J, that is also assumed to be rigid. And the flexible strength length, this length, the length LC is the flexible length for the case of rigid in factor. The rigid zone offset never affect the axial and torsional deformation, but it affect the bending and shear deformation. So the full developed elemental length is assumed to be flexible for this deformation, like axial and torsional deformation. But in case of shear deformation and bending, the clear length or the flexible length is assumed to be calculated. So if we look into the ETABS, the default value for the rigid is 0. The maximum value is unity. It means the rigidity factor lies between 0 to 1, 0 to 1, and we may find, or the user may find, a suitable value in between 0 to 1. And we must use the engineering judgment to select the appropriate value for this parameter. And it depends on the geometry of the connection and may be different for different elements that frame into a connection. Typically, the CSI, Computer Science Structure Incorporation, recommends the value of 0.5 for rigid factor as a rigid factor in the case of RCC as well as steel. The value of R is 0.5, somewhere in between this 0 and 1, suppose here. This is the portion of the length that is considered for the analysis for shear and bending. So this is the value of R rigid zone factor in structural analysis softwares. If we turn into the ETABS or SHAF, now let me go to ETABS. Here, go to assign frame. The model is run. I will unlock this model and show the way how to define the rigid in offset, rigid zone factor in the analysis. Go to assign frame. Here we see the rigid in offset, and here a frame assignment in length offset. This dialog box appears, and the length of end offset can be defined in two ways. The first way is automatic from the connectivity, and the second way is to define the length manually. If we define the length manually here, and the analysis is based on according to the length, the bending moment and shear deformation depends on the on this length. And if the length is determined from auto connectivity, it means the SAP or ETABS graphical user interface, it automatically detects the length at the node I and J, J within itself from the cross section. Suppose we have the cross section of beams of 230 by 300 mm and the columns of 300 by 300 mm, and the rigid, the inline offset for the beams, if we check the beam, it is 150 mm from the center of the column to the face of column. If we go to the inline offset assigned to the beams, automatically it determines the value of 150 for the beams as well as column. If we look into the column as well, we see the same value. Sorry, the columns is 350. It means it is at the base of the beams. The beams depth of the beam is 350 mm and it is 350, and end I is 0. End I is 0 means this is, suppose the end I is at the base and it is 0 and it is 350 mm from the base of the column. If we see the bending moment and shear force diagram for this structure, we will get, suppose like this for the beams. I mean 150 mm from the center of the columns, and for the columns it is like this, 350 mm below the beams, and or the soffit, from the soffit level of the beams to the base. This value indicates this, and if you go to the beams, it is 350 by 350 mm, and sorry, it is 150 by 150 mm at the from the center of the columns. So it is a in length offset. And if we go to rigid zone factor for this model, we put the rigid zone factor of 1 to check the analysis. Here I model the same frame with 5 different rigid wind offset or rigid zone factor assigning. The first one is the rigid zone factor is considered as 0 and no panel zone. It means no panel zone. The length is taken from this edge. I mean the in length offset. I model it as automatic, determined by the joint connectivity of the frame section. The second one is the rigid zone factor is modeled as 1 and with no panel zone. Here the rigid zone factor is 1 and with no panel zone. We see 1. But if we see the first figure, the rigid zone factor is 0, and the third one is the rigid zone factor of 0.5 with no panel considering for both beams and columns, and the fourth one indicates the rigid zone factor of 0, rigid zone factor of 0.5, and the in length offset is 0. And similarly, the final one is the rigid zone factor of 0 and the in length offset is also 0. So we will see the deviation, or we will see the difference in the response of the structure. So let me run this model. Okay, the model has been analyzed. And before analyzing the structure, I forgot to say that the load of lateral load of 10 kilonewton is assigned at this joint for all the structure in order to see the deflection and bending moment of the structure. So let me go to the deflection. In the case of lateral load, let me click apply. Okay. And if we go to the deflection of this point, where the rigid zone factor is modeled at 0, the deflection is 1.182. It means the length for this model is LC. The length is considered from the face of the column. If the length is small, the stiffness value will be higher and the time period will be lower. And resulting is the deflection of 1.182 mm. And if we look into this model, which has assigned as a rigid zone factor of 1, it means the structure is fully rigid. The length or full length from center to center is considered in this case. I mean the stiffness tends to decrease. So let me turn into this model. There are altogether 5 models for different application of rigid in zone or in length offset. The first case is considered as rigid zone factor tends to be 0. If we check, let me check. These are the beams and column of 230 by 350 beam section and column section of 300 by 300 section mm, and a lateral load of 10 kilonewton is applied at this node. So this is the lateral load applied for this 2D frame. And the first case is the case. This is the case with a rigid zone factor equals to 0 in ETABS. If we go here, this is by default screen, and there are 2 way to define the end offset along the length. The first one is automatic from connectivity, and second one is to define length. And the rigid zone factor equals to 0. And if we look into this model here in the first case, The in-length offset as the connectivity from auto connectivity is yes, and the offset is 150 at both nodes. It means the column size is 300 by 300 and the offset is from the center to the inner face of the column. It means 150 from the both ends, and the rigid zone factor equals to 0. If we look into the rigid zone factor, this is the case of rigid zone factor. It means the total length equals to the length from center to center of the column. It means the increase of length. The increase of length means the decrease in stiffness and the increase in deflection value. If we look into this relation, this is the global stiffness matrix, and the stiffness value depends upon the L. If EI and I are constant, and the stiffness value is fully depending on the L length parameter for its evaluation. So if the length of the structure is or the element is increased without considering the rigid in factor or zone factor at 0, full length is utilized, so the stiffness tends to decrease, resulting in the increment of the deflection. We see the deflection is 1.182 for this case, which neither utilize the panel zones nor rigid offset, and the deflections are the largest, more conservative, and moments are the smallest. We'll see the moment at the beam is 5.7013, and the deflection is 1.182 for this case. We check in ETABS as well. Let me run the structure again. Let me run this. And in the first case, the deflection is higher, 1.182 We see 1.180 And looking into the second model, it is considered as rigid zone factor of 1. It means the length of the beams taken for the stiffness calculation is LC minus the length of beam from center to center minus total length of offset at both ends. It means the length is decreased and the stiffness value is increased. Length is decreased here, then K value is increased, resulting in low deflection, less value of deflection as compared to figure model 1. Then delta tends to decrease as compared to figure 1. So let me run this model again. The deflection of this case, first one is 1.180 and let's check the deflection in the second case. It means in the second case, the deflection is decreased to a value of 0.966 and let's check the bending moment as well. Let's check the bending moment 33. Okay, the bending moments also low in first case, whereas there is a highest or more bending moment as compared to the first case in second one in the beams, and low in the case of column. The bending moment is not much significant as compared to the beams for the columns. Okay, this is the second figure, case second. This is the case second. The rigidity factor is considered as 1. It means this portion is excluded. It means the structure is fully rigid and the length of overlap is also increase the stiffness of the structure, because in case of rigidity zone factor equals to 1, the cross-sectional element in the junction overlaps. So the deflection is 0.97 and it implements the fully rigid offset beams and columns. This technique is not recommended because the smallest and the conservative deflection result for the moment values are higher and the conservative. So let me turn into third case. The third case is the rigid zone factor is modeled at 0.5. If the rigid zone factor is modeled here, the structure is fully stiff, rigid, and if the rigid zone factor is considered as 1, the structure is fully rigid, and 0, the structure is not fully rigid, and this is the point somewhere between the 0 and 1, I mean 0.5. The structure is the joint is assumed to be flexible or less rigid as compared to the value incorporated as 1. In this case, the maximum deflection obtained is 1.07 mm. It implements the 50% rigidity at the beams and column junction, and the CSI or the designers recommends to use this value for realistic demand in case of both steel and RCC structure. Let me turn into ETABS model. Yeah, this is the third model, and if we see the bending moment, it is somewhere in between the first two models. In the first model, it is 5.70, and in the second 6.43, and the bending moment is also somewhere in between these two values, and the deflection is also between the two values. In the first value, the deflection is 1.18, whereas in the second model, the deflection is 1.18. In the second model, it is 0.979, and in this model, it is 1.07 mm. It means it is somewhere between the value assigned as 0 and the value assigned as 1 regarding to the rigid zone factor. And these two figures, these two models indicate the in length offset or of 0. I mean, if we check this structure, the in length offset, they are selected to manual tab, and it is 0, and the rigidity factor is 0.5. And in this case, the in length offset is 0 and the rigidity factor is also 0. So let me check the bending moment diagram for these two as well for the lateral load. The bending moment diagram is, the bending moment is same as like of incorporating the R value of 0.5. So this is the case of considering R value as 0.5, rigidity factor as 0.5. Here we see the bending moment at the beams is 6.073, and here also the similar bending moment in the beams. In this also, in the last one also, the bending moment is similar, and the deflection is also similar. I think. Let me check the deflection. Sorry. Case lateral load. So the deflection is 1.182, 1.182, and the deflection is similar to the first case. So the bending moment is 0, is similar to the second phase. If so, the difference is only in the appearance of the bending moment. It is from the center line of the beams column assembly. These two figures indicate the bend, represent the bending moment and shear force diagram from the center line. Whereas if we consider the in length offset, it considers the bending moment from 150 mm away from the center line, but the values are similar. So these three values of bending moment for the beams are similar. So let's summarize the result. Here, in first case, rigid zone factor equals to 0, no panel zone. And deflection is 1.182 mm and bending moment is 5.7013. The second case is rigid zone factor is modeled as 1 and no panel zone. Deflection decrease and the increase in the bending moment. The third case and the recommended case is R factor at 0.5 with no panel zone, and the deflection lies in somewhere in between these two values. And remaining the two cases for the rigid zone factor equals to 0.5 and 0, L equals to LC. The deflection is 1.182 and the bending moment is similar to that of rigid zone factor applied or assigned at 0.5. So in summary, if the user defined rigid offset length option for model 1 were set to 0, which we have done in the fourth and fifth model, rather than the default setting based on the connectivity, result would be identical except that moment values would be reported at the end of the member. If the in-length offset were kept at 0, or it is some distance what according to the sections governs, the moment value would be identical but reported at the end of the member and from the offset of the members, and not at the face of the columns and beams. Concrete frames should never use a fully rigid zone. A value of 0.5 is recommended for concrete frame where 50% of the actual offset is considered rigid. So rigidity only affects the bending about the two axis and not the axial, and bending as well as shear deformation about the axis, but not the axial and torsional properties of the structure. So in the next video, I'll try to model the same thing with including the panel zones in ETABS for concrete structure. There are different ways to model the joint panel. If we look into the joint, suppose assign joint, here is panel zone, and this is the panel zone data dialog box, and the values should be incorporated for each of these. So it is easy in case of steel because auto-elastic properties can be considered in steel structure, but in the case of concrete structure, the value of this link property as well as this user-defined nonlinear properties and the other parameters, they have to be assigned manually with the calculation. So I'll try to cover these things in the upcoming videos. Till then, keep watching, like, share, and comment. Thank you.